if the oldest story we've ever told wasn't the beginning at all? What if, etched into the very bedrock of our planet, hidden within the fossilized remains of ancient life, lies a narrative far grander, far more awe-inspiring than anything our myths could conjure? For generations, across every culture and continent, humanity has been captivated by the idea of giants, colossal beings, monstrous creatures, or even enormous versions of ourselves, traversing the primordial landscapes of a forgotten Earth. This enduring fascination, woven into the fabric of our oldest legends and whispered around countless campfires, begs a profound question. Were there literal giants on ancient Earth? Did beings of immense scale truly dominate our planet's nascent stages, shaping its very evolution long before humanity's fleeting arrival? Modern science, ever so carefully peeling back the layers of geological time, offers tantalizing glimpses into this possibility, distinguishing between the ephemeral whispers of myth and the undeniable echoes of scientific evidence. It's a journey not just through time, but through the very essence of existence itself, a quest to uncover the true first inhabitants of a world we are only just beginning to understand. If you find yourself enjoying such profound explorations into our planet's past, please consider subscribing. The human mind, whether in its nascent stages of storytelling or its most advanced scientific endeavors, has always gravitated towards the colossal. From the towering titans of Greek mythology, who once waged war against the Olympian gods, to the Nephilim described in biblical texts, often interpreted as giant offspring of heavenly beings and human women, the archetypal giant looms large in our collective consciousness. Across cultures, folklore recounts tales of frost giants guarding icy realms, mountain giants embodied in the very peaks they inhabit, and benevolent giants shaping the landscape with their immense strength. These narratives, rich with symbolism and wonder, speak to a primal human awe in the face of overwhelming scale and power, often reflecting a pre-scientific attempt to explain inexplicable geological formations or powerful natural phenomena. Yet, the pattern persists. An inherent human need to imagine beings greater than ourselves, to populate the wild, untamed corners of our world and our past with something truly immense. But what do we truly mean when we speak of giants in a scientific context? Are we constrained by the anthropomorphic visions of our myths, or does the term expand to encompass something far more profound? Modern science draws a crucial distinction, moving beyond the realm of mythological humanoids to embrace a broader definition rooted in paleontology and evolutionary biology. Here, giant refers not just to extraordinary size within a species, but to organisms that push the boundaries of biological possibility, often reaching dimensions unprecedented in their respective ecosystems or entire eras. This shift in perspective allows us to consider a staggering array of ancient life forms, from colossal invertebrates that once scuttled across primordial seafloors to the awe-inspiring megafauna that roamed continents millions of years later. The debate remains unresolved in popular imagination, yet science endeavors to clarify. The journey to understand ancient Earth's inhabitants begins not with titans or mythical beasts, but with something far more fundamental, far more ubiquitous, and utterly foundational: the microscopic. Billions of years ago, on a nascent Earth radically different from the one we inhabit today, life emerged. It was not the complex multicellular organisms we recognize, but single-celled prokaryotes, the simplest forms of life, that first colonized our planet's primordial oceans. These ancient pioneers, appearing sometime around 3.8 to 3.5 billion years ago, began a slow, deliberate transformation of an entire world. They formed stromatolites, layered structures created by colonies of cyanobacteria, which are essentially fossilized microbial mats. These unassuming structures, still found in some parts of the world today, are enduring testaments to the earliest forms of life, silently altering the very chemistry of our planet. For an unfathomably long span of Earth's history, spanning billions of years, microbial communities held absolute dominion. It is easy, from our vantage point of macroscopic complexity, to overlook the profound significance of this microbial age. Yet, the story of life on Earth is irrevocably tied to these tiny invisible architects. Their most famous act of macroscopic environmental engineering was the Great Oxidation Event, a planetary transformation propelled by the oxygen-producing photosynthesis of cyanobacteria. This gradual yet revolutionary influx of free oxygen into the atmosphere and oceans triggered a cascade of changes, from mass extinctions of anaerobic life to the formation of the ozone layer, paving the way for the eventual emergence of more complex oxygen-breathing organisms. The silence of these billions of years, dominated by invisible life, shaped the very foundation upon which all subsequent diversity, including giants, would eventually stand. It is as if the planet itself had to breathe oxygen first before it could dream of growing anything truly massive. The path from invisible microbes to visible giants was a long and arduous evolutionary trek, punctuated by critical turning points. One of the most dramatic infusions of complexity and scale occurred during the Cambrian explosion, approximately 541 to 530 million years ago. This relatively brief geological period, a mere blink in Earth's vast timeline, witnessed an unprecedented diversification of multicellular life forms, marking the emergence of nearly all major animal phyla we recognize today. It was a benchmark for complex life, a sudden flourish of anatomical innovation and ecological differentiation. Gone were the days when simple, soft-bodied organisms dominated. Now, creatures developed hard shells, skeletons, and specialized sensory organs. It is as if life, having experimented with the invisible for eons, suddenly discovered the infinite possibilities of diverse, visible forms. Within this evolutionary burst, the concept of giant began to take shape, particularly in the marine realm. Among the most iconic early large marine predators was Anomalocaris, meaning anomalous shrimp. Reaching lengths of up to 1.8 meters, for its time, Anomalocaris was truly gigantic. With its large compound eyes, formidable grasping appendages, and a circular mouth lined with sharp plates, it was the apex predator of the Cambrian seas, navigating the complex ecosystems that were rapidly evolving. Its size was an evolutionary advantage, allowing it to prey on the newly evolved armored forms, demonstrating how increased scale provided an edge in a world where predation had become a primary selective pressure. The evolutionary pressures were fierce, an arms race between predator and prey, where bigger bodies, stronger armor, and more efficient hunting strategies drove organisms to larger sizes. This concept, where environmental factors drive organisms to greater scale, would echo throughout the ensuing eons. The Cambrian, the subsequent geological eras, witnessed an unparalleled explosion of gigantism, particularly during the Mesozoic era, often referred to as the Age of Reptiles. This era, spanning from approximately 252 to 66 million years ago, and divided into the Triassic, Jurassic, and Cretaceous periods, is synonymous with creatures of unfathomable scale. If we are searching for literal giants that once walked our planet, this is where the truth unequivocally manifests. The dinosaurs, in their astonishing diversity and often immense proportions, embody the very essence of archaic giants. Their reign was long and spectacular, and modern science continues to unravel the mysteries of their colossal existence. The iconic giant dinosaurs immediately spring to mind. Among the largest terrestrial animals to ever walk the earth were the sauropods, long-necked, long-tailed herbivores that include titans like Argentinosaurus, potentially weighing up to 100 tons and stretching over 30 meters in length. Their sheer bulk allowed them to process vast quantities of vegetation, a strategy that, like the earliest microbial mats, was critical for their survival. Then there were the theropods, the fearsome bipedal carnivores, dominated by the legendary Tyrannosaurus rex, a predator measuring up to 12 meters long and weighing several tons, with teeth capable of crushing bone. Yet there are marine reptiles, not dinosaurs but contemporaries, that also reached immense proportions, such as the mosasaurs, ocean-dwelling predators that could exceed 17 meters in length, essentially dragon-like leviathans of the ancient seas. The silence of these magnificent creatures is now only broken by the whispers of paleontological discovery. What enabled such astonishing gigantism? Historians are still debating the precise interplay of factors, but several key elements contributed to the dinosaurs' immense size. The relatively stable and warm climate of the Mesozoic, coupled with abundant plant resources, provided a consistent food supply to fuel such enormous bodies. High levels of atmospheric carbon dioxide supported lush vegetation, ensuring a rich biosphere. Their unique physiology, particularly for sauropods, with their efficient avian-like respiratory systems and bones filled with air sacs, allowed for both support and light weight relative to their immense size. The lack of mammalian competition for large herbivorous niches, due to mammals remaining small and nocturnal for most of the Mesozoic, also played a significant role, allowing dinosaurs to occupy and dominate the largest ecological roles. It is as if the environmental conditions of the Mesozoic were perfectly calibrated for the evolution of true giants. Following the cataclysmic extinction event that ended the Mesozoic era approximately 66 million years ago, paving the way for the Cenozoic, the age of mammals truly began. With the departure of the non-avian dinosaurs, an ecological vacuum emerged, leading to a rapid diversification and radiation of mammalian life. Over the course of the Paleogene and Neogene periods, mammals exploited newly available niches, with many lineages evolving into colossal forms, often mirroring the grandeur of their reptilian predecessors. These mammalian megafauna represent a distinct phase in the story of Earth's giants, connecting the profound depths of geological time to ancestors that, while ancient, feel somewhat closer to the present day and even to human history. Consider the giants of the Cenozoic, massive creatures that populated diverse landscapes. The woolly mammoths, iconic residents of the Ice Age, with their towering size, great tusks, and shaggy coats, roamed vast grasslands across the northern hemisphere. Contemporaneous with early humans, their immense size was an adaptation to cold climates and a defense against predators. Then there was Megatherium, the giant ground sloth, an astonishing creature that stood up to 6 meters tall on its hind legs and weighed several tons, capable of browsing on high branches. From the ancient forests of Eurasia, we find Indricotherium, also known as Paraceratherium, a hornless, rhino-like creature that was perhaps the largest land mammal to ever exist, standing over 5 meters tall at the shoulder and weighing up to 20 tons. These creatures, varied in form and function, were undeniably giants of their era. What if these behemoths were still among us? Yet the pattern persists. Even these colossal mammals eventually faced extinction. While the exact causes are still debated, a combination of factors, including rapid climate change, habitat loss due to glacial cycles, and increasingly, the impact of early human hunting, contributed to their decline. The disappearance of much of the mammalian megafauna marks a significant turning point, leaving a world largely populated by smaller, more adaptable creatures, and setting the stage for the relatively recent emergence and dominance of humans. The silence that followed their departure echoes across the plains and forests they once inhabited. Ultimately, the persistent whispers of human-like giants in our ancient myths, echoing across cultures from Nordic sagas to indigenous creation stories, stand in stark contrast to the scientific record. While every culture seems to possess a narrative of enormous humanoids, often attributed with supernatural strength or primitive savagery, the paleontological and archaeological evidence offers a decidedly different picture. There is no substantiated scientific evidence of a past race of human giants of the scale depicted in folklore. While occasional individuals throughout history may have grown unusually tall due to medical conditions such as gigantism, these isolated cases do not constitute an entire species or widespread population of colossal human beings. The debate remains unresolved in the popular imagination, yet science endeavors to clarify this distinction. The true giants of ancient Earth were not overgrown versions of ourselves, but a breathtaking procession of life forms, each perfectly adapted to its time and place, pushing the boundaries of scale and existence. The story of life on Earth, from its primordial microbial beginnings through the Cambrian explosion's diversification to the awe-inspiring reign of dinosaurs and the subsequent rise of mammalian megafauna, is a testament to the colossal potential of evolution. It is a narrative stitched together by immense geological forces and microscopic genetic shifts, a slow but relentless journey towards ever greater complexity and, at times, ever greater size. Modern science peels back the layers of Earth and time, revealing a truth that is both grander and more intricate than any myth. Life itself, in its boundless capacity to evolve and adapt, is the ultimate giant, ABE, force that has shaped and reshaped our planet over eons. The silence of these vast epics, filled with unseen wonders and unfathomable scale, speaks volumes. We, humanity, are relatively recent arrivals on this ancient stage, a species of comparatively modest stature in the grand scheme of Earth's history. The fossil record. They were the microbes that forged our atmosphere, the early multicellular marine predators that first understood the concept of scale, and the Mesozoic reptiles and Cenozoic mammals that pushed the very limits of terrestrial and aquatic gigantism. What if, instead of focusing on human-like giants, we embraced the reality of these magnificent biological titans? The possibility that colossal beings once traversed our planet is not merely a myth, but a paleontological certainty, a breathtaking truth revealed by the diligent work of science. The story of our world's past is rich with wonders, and the truth about its first inhabitants, the true giants, is far more compelling than any fiction. If this journey through Earth's colossal past sparked your imagination, remember to engage with the video, perhaps share your thoughts in the comments, and consider subscribing for more explorations into the profound mysteries our world holds. And indeed, it's not just the sheer physical size of these ancient beings that is awe-inspiring, but the incredible adaptations they honed to achieve and sustain such dimensions. Consider the sauropods, those long-necked, long-tailed herbivorous dinosaurs that represent the pinnacle of terrestrial gigantism. How did a creature weighing perhaps 70 tons or more, like an Argentinosaurus, manage to stand, walk, and even thrive? Their skeletal structures were not merely scaled-up versions of smaller animals, they were elegantly engineered marvels. Their bones, often pneumatic, filled with air sacs much like birds, were strong yet surprisingly light, reducing overall weight while maintaining structural integrity. Think of it as nature's own advanced composite material. This internal scaffolding wasn't just for weight reduction, it also played a role in their respiratory system, ensuring efficient oxygen uptake to fuel their massive metabolisms. Their hearts, too, must have been colossal, pumping blood hundreds of feet, vertically, to reach their brains. The sheer hydraulic pressure required is almost mind-boggling. Some researchers speculate about auxiliary booster hearts along their necks, or perhaps a unique vascular system that leveraged muscle contractions and valves to aid circulation. And what of their digestive systems? To fuel such immense bodies with vegetation, they would have needed processing plants of incredible capacity. We're talking about digestive tracts the size of small rooms, harboring vast microbial communities to break down tough plant matter. They would have spent a significant portion of their lives eating, transforming entire landscapes as they browsed. Imagine herds of these giants, denuding forests and grasslands, their very existence shaping the ecological fabric of their world. Their impact on nutrient cycling, seed dispersal, and even the geological record through their immense waste production would have been profound. They weren't just big animals, they were ecosystem engineers on a scale we can barely fathom today. And then there's the question of reproduction. How does an animal of such magnitude reproduce? Laying eggs the size of basketballs or more, burying them in massive clutches, and likely relying on environmental heat for incubation. The survival rate must have been low, but their sheer numbers, sustained over millions of years, speak to a highly successful strategy. From their coordinated movements suggested by trackways to their potential social structures implied by herd formations in fossil evidence, they represented a level of complex adaptation to gigantism that modern animals simply don't approach. They were not merely big, they were masters of being big. But gigantism wasn't solely the domain of the land. In the vast, boundless oceans, even greater champions emerged. The whales, particularly the baleen whales, are a testament to the fact that the largest animals ever to exist on Earth still swim in our seas today. While dinosaurs dominated the Mesozoic, they pale in comparison to the blue whale, which can reach lengths of over 100 feet and weigh up to 200 tons. This leviathan represents not just impressive size, but an entirely different evolutionary pathway to gigantism, one deeply intertwined with the properties of water. Water's buoyancy liberates aquatic animals from the crushing weight that terrestrial creatures must constantly battle. This allows for immense body mass without requiring the same robust skeletal framework. A whale's bones are dense, but their overall structure is hydrodynamic rather than rigidly load-bearing, enabling incredible flexibility and streamlining. The evolution of filter feeding in baleen whales is another critical adaptation. Instead of expending vast amounts of energy chasing and grappling with individual prey, they simply open their cavernous mouths, take in prodigious volumes of water, and filter out tiny crustaceans and small fish, a vast, accessible food source. This energy-efficient method of feeding, combined with the buoyant support of water and the ocean's vast food webs, created the perfect conditions for these marine giants to evolve. The blue whale's heart is the size of a small car, yet its pulse rate can slow to mere beats per minute during deep dives, conserving oxygen. Their lungs are enormous, allowing them to hold their breath for extended periods. Their calls, the deepest in the animal kingdom, can travel thousands of miles through the ocean, a testament to their incredible communication capabilities across vast liquid landscapes. They have mastered an environment that is both nurturing and challenging, evolving a blend of massive size and nuanced physiological control that is truly breathtaking. The journey to gigantism, whether on land or in the sea, is never without its challenges and limitations. Physics, physiology, and ecology all conspire to set boundaries. For terrestrial animals, the square-cube law is a constant adversary. As an animal's dimensions increase, its volume, and thus its weight, increases by the cube, but its cross-sectional area, and thus the strength of its supporting bones and muscles, only increases by the square. This means that larger animals need disproportionately thicker limbs and stronger skeletons just to support their own weight. There's a point where the structural integrity of bone, even optimally engineered bone, simply cannot bear further increases in mass. This might explain why land animals haven't significantly exceeded the size of the largest sauropods. Beyond that, maintaining mobility and avoiding bone fracture might become insurmountable. Heat regulation is another major hurdle. Larger bodies have a smaller surface area to volume ratio, meaning they retain heat more efficiently. While this can be advantageous in cold climates, in warm environments, overheating becomes a serious threat. Giants like sauropods likely employed various strategies, from their long necks and tails acting as radiators to behavioral adaptations like seeking shade or even physiological mechanisms to regulate blood flow to the surface of their skin. Elephants today use their large ears for this very purpose, fanning blood through them to dissipate heat. Weight is less of an issue. Food availability remains a critical factor. The vast quantities of krill and plankton required to sustain a blue whale depend on productive ocean upwelling zones. Shifts in ocean currents, climate change, or overfishing of their prey can have devastating impacts on their populations, as we've seen with the historical whaling industry. The sheer metabolic demands of a colossal body mean that even a slight imbalance in their ecosystem can have cascading, detrimental effects. Beyond the biological realm, there's also the fascinating intersection of gigantism with geological and atmospheric conditions. Early Earth, particularly during the Carboniferous period, saw the rise of enormous insects like Meganeura, a dragonfly with a wingspan of over 2 feet. This was largely attributed to higher atmospheric oxygen levels, up to 35% compared to today's 21%. Higher oxygen allowed for more efficient diffusion into their tracheal respiratory systems, which lack active pumping mechanisms like lungs. As oxygen levels declined, so too did the maximum size of insects. This illustrates how even subtle changes in planetary conditions can dramatically influence the potential for life to reach colossal scales. The very landscape itself has borne the marks of giants. The fossilized trackways of sauropods reveal not just their individual movements, but also hints at herd dynamics, migration patterns, and the sheer force with which they impacted the ground. Imagine the thundering sound, the seismic tremor, as a herd of long-necked titans moved across a primordial plain. Their weight could compress the soil, influencing drainage patterns and localized vegetation growth. Their massive consumption of plant matter undoubtedly shaped forest composition and nutrient distribution. They were, in essence, living earth movers, impacting their ecosystems on a grand scale over millions of years. And it's not just the living giants. The very concept of gigantism forces us to confront the immense timescales of Earth's history. These creatures didn't just appear fully formed, they were the product of millions upon millions of years of gradual accumulation of advantageous traits. It's a testament to the slow, relentless power of natural selection, often playing out over spans of time so vast that they defy human comprehension. Each fossil discovery, each bone fragment, each trackway is a window into a world that operated on fundamentally different metrics of scale and time. This journey through deep time and colossal life forms also inevitably leads us to ponder the nature of extinction. The very conditions that favored the rise of giants could also, just as readily, lead to their downfall. Climate shifts, volcanic eruptions, asteroid impacts. These global catastrophic events, particularly the one 66 million years ago that ended the reign of the non-avian dinosaurs, illustrate the fragility of even the most dominant life forms. The scale of the giants made them especially vulnerable in some respects. Slow reproductive rates, specialized diets, and massive energy requirements could turn small environmental changes into existential threats. Yet, life, in its endless resilience, found new pathways. The void left by the dinosaurs was eventually filled by the mammalian megafauna, and in the oceans, whales continued their evolutionary march toward unparalleled size. Our fascination with giants is not merely about their physical dimensions. It taps into something far deeper within the human psyche, a sense of wonder, a humbling recognition of forces greater than ourselves, and perhaps a faint echo of our ancient past when the world truly was populated by awe-inspiring behemoths. It's a reminder that our perception of normal is entirely dictated by our current epoch. For hundreds of millions of years, the Earth was a realm where creatures of immense size were not the exception, but in many ecosystems, the rule. So when we speak of giants, let us broaden our conceptual lens. Let us move beyond the anthropocentric myths of towering humanoids and embrace the staggering, scientifically validated truth of Earth's biological history. The real giants were not fantastical beings of myth, but tangible, breathing, roaring, and swimming entities that left their indelible mark on our planet. They were the evolutionary masterpieces of their respective eras, pushing the boundaries of what is physically possible for living organisms. The story of gigantism is ongoing. Even now in our modern world, we contend with the sheer scale of blue whales, the impressive bulk of elephants, and the imposing presence of giant sequoia trees, the largest single organisms by biomass on Earth. These living giants continue to shape their environments and capture our imaginations, serving as a powerful link to the colossal past. They are living laboratories of evolutionary adaptation, demonstrating that the drive towards immense size within the bounds of physical and ecological constraints is a recurring theme in the tapestry of life. Consider the role of size in evolutionary competition. Often, larger size confers advantages, deterring predators, access to more food resources, or the ability to dominate territories. But it also comes with increased energetic demands, slower reproduction, and potentially greater vulnerability to environmental shifts. The ebb and flow of gigantism throughout Earth's history is a complex dance between these advantages and disadvantages, constantly shaped by changing planetary conditions. It's not a linear progression towards ever larger forms, but rather a dynamic process of adaptation and diversification. And what about the deep psychological impact of these giants on our ancestors? While they never encountered a living sauropod, early humans coexisted with megafauna like mammoths, woolly rhinoceroses, and giant ground sloths. These were formidable creatures capable of inspiring both awe and terror. It's not a stretch to imagine that the encounters with these immense animals, the discovery of their colossal bones, or the contemplation of their existence could have fueled the very foundation of mythological giants. The stories of titans and cyclops, primordial serpents and monstrous beasts, might be distant echoes of ancestral memories, filtered through generations and embellished with cultural narratives. The real giants of our past could have thus indirectly shaped human culture, art, and storytelling, even if their direct impact on myths is hard to prove definitively. The study of these ancient titans isn't just about cataloging giant bones. It's about understanding the very machinery of life. Paleontologists, biologists, and geologists collaborate to reconstruct living worlds from fragmented evidence. They use biomechanics to model how these animals moved, grew, and even breathed. They examine fossilized gut contents and tooth-wear patterns to infer diets. They analyze stable isotopes in bone to understand climates and ecosystems. It's a monumental scientific detective story, continually revealing new insights into the incredible diversity and adaptations of life on Earth, boundaries of our understanding of evolution and the planet's history. The finding of a new super-heavy sauropod like Patagotitan majorum in Argentina, or the discovery of immense marine reptiles like Ichthyodotan severnensis with jaws potentially 5 times longer than a blue whale's, forces us to continually adjust our mental image of Earth's past. These aren't just bigger numbers, they represent new physiological thresholds, new ecological roles, and new chapters in the saga of life that dared to be truly colossal. The beauty of these scientific revelations lies in their grounding in reality. They offer something far more profound than any fictional tale, the genuine, awe-inspiring truth of Earth's monumental past. It's a reminder that our planet has always been a stage for extraordinary life, a testament to the endless creativity of evolution. And by celebrating the true giants, we gain a deeper appreciation for the boundless potential of life, for the incredible diversity that has flourished here, and for the astonishing history that precedes our own brief moment in time. So, the next time you cast your gaze upon a massive mountain range, or stand before the vast expanse of the ocean, or even feel the rumbling passage of a large modern vehicle, take a moment to reflect. Think of the immense energy, the incredible physiological adaptations, and the millions of years of evolutionary struggle that went into creating the largest beings this planet has ever known. Think of the world they inhabited, a world where the colossal was commonplace, where the ground shook with the footsteps of titans, and where the oceans teemed with leviathans. This exploration of gigantism isn't just about the past, it's about understanding the present and contemplating the future. What are the limits of size for modern life? Will environmental pressures lead to a decline in body size, or could new ecological niches someday favor the evolution of new giants? While speculative, these questions highlight the dynamic nature of life on Earth. The story of giants is a continuous narrative written not just in the ancient rocks, but also in the living world around us. And perhaps in understanding and appreciating the true giants of our planet, from the ancient microbes that oxygenated our atmosphere, setting the stage for all complex life, to the towering sequoias and the majestic whales of today, we can also gain a better perspective on our own place in the grand narrative. We are part of this incredible lineage, a species that, though physically modest, possesses the unique ability to unravel the mysteries of our colossal past. Our curiosity, our technological prowess, and our shared desire to understand the universe around us allow us to resurrect these magnificent beings in our minds, to learn from their incredible stories, and to marvel at the sheer boundless wonder of life itself. The silent giants of Earth's history continue to speak to us. If we only know how to listen to the whispers carried on the winds of deep time, embedded in fossilized bone and echoing through the vast open spaces they once commanded. This dialogue with the ancient world enriches our present and deepens our appreciation for the extraordinary journey of life on our pale blue dot. And in truly appreciating these whispers, we begin to understand that gigantism isn't a singular phenomenon, but a multifaceted tapestry woven with threads of ecological opportunity, biological imperative, and sheer luck. It's a testament to the boundless creativity of evolution, a grand experiment played out on a planetary scale. Each giant, whether a sauropod or a blue whale, represents a pinnacle of adaptation, a highly specialized organism that found a way to thrive at the very edge of physical possibility. They pushed the boundaries of structural integrity, metabolic efficiency, and environmental tolerance. Consider the sauropods, those long-necked marvels that roam the Mesozoic. Their secret to such immense bulk wasn't just about big bones, it was a symphony of interconnected adaptations. Hollowed-out vertebrae, pneumatic bones, akin to those found in birds, significantly reduced their skeletal weight while maintaining immense strength. This was a critical innovation, allowing them to support their gargantuan frames without collapsing under their own mass. Their long necks, sometimes reaching unimaginable lengths, weren't just for reaching high foliage. They were sophisticated feeding platforms. Imagine a mobile, self-propelled harvesting machine able to sweep across vast swathes of vegetation with minimal body movement, thus conserving precious energy. Their digestive systems must have been equally specialized, vast fermentation vats capable of processing colossal quantities of tough plant material, extracting every last calorie. It's theorized they may have had multiple stomachs, much like modern ruminants, but on a scale that defies easy comprehension. And their hearts, oh, their hearts, to pump blood all the way up those towering necks to their brains, they must have possessed incredibly powerful multi-chambered organs, generating immense pressure to counteract gravity's relentless pull. Some paleontologists even suggest auxiliary booster hearts along the neck, although this remains an area of debate and fascinating speculation. Each breath these titans took was a monumental effort, their lungs likely requiring enormous volume and efficiency to oxygenate such a vast body. Their sheer reproductive strategy would have been equally remarkable, needing to lay hundreds if not thousands of eggs throughout their lifespan, just to ensure a few offspring survived to reach maturity and continue the lineage. The energy budget for these animals was mind-boggling, a constant battle against entropy on an epic scale. Then there are the marine giants, the whales. Their shift to an aquatic environment fundamentally changed the rules of the game. Buoyancy became their ally, effectively negating much of the gravitational stress that limits terrestrial giants. This allowed evolution to push the boundaries of size even further. The blue whale, the largest animal ever known, exemplifies this. Its streamlined body, designed for effortless hydrodynamics, allows it to glide through the ocean with remarkable efficiency. Its baleen plates, a marvel of bioengineering, enable it to filter feed on vast quantities of krill, turning tiny organisms into an enormous biomass. This feeding strategy, known as bulk filter feeding, is incredibly energy efficient, allowing them to exploit a vast, abundant food source without expending massive amounts of energy chasing individual prey. Their lungs are massive, allowing them to hold their breath for extended periods and dive to great depths. Their bones, unlike the hollow bones of sauropods, are denser, acting as ballast aiding in diving and stability. Surface. The communication systems of whales, their complex songs traversing vast oceanic distances, speak to a level of sociality and intelligence that continues to fascinate and humble us. These giants are not just big, They are intricately, exquisitely adapted to their marine world, every fiber of their being optimized for life in the deep blue. And it's not just the vertebrates. Consider the colossal squids, lurking in the abyssal depths, their eyes the size of dinner plates, designed to capture the faintest glimmer of light in a world of perpetual twilight. Or the ancient arthropods like Arthropleura, a millipede-like creature that grew to over 6 feet long during the Carboniferous period. Its gigantism was likely fueled by an atmospheric oxygen content significantly higher than today's, allowing for more efficient respiration through their spiracle systems, which are less efficient at oxygen uptake than lungs. When oxygen levels dropped, so too did the size of these invertebrate giants, a stark reminder of how environmental factors continuously sculpt the boundaries of life. The concept of gigantism, therefore, is intimately entwined with the concept of environmental opportunity. When resources are abundant, competition is low, or predators are absent, evolution can take a different path, favoring size as an advantage. Bigger animals often have an easier time regulating their body temperature, Bergmann's rule, can defend themselves more effectively, and can outcompete smaller rivals for resources. But there's always a trade-off. Extreme size also brings vulnerabilities. Slower reproduction rates, higher caloric demands, and increased susceptibility to environmental shifts are often the price of being a giant. A slight change in climate, a reduction in food availability, or the emergence of a new predator can spell disaster for a species that has invested so heavily in sheer biomass. The dinosaurs, for all their majesty and dominance, eventually succumbed to a catastrophic environmental event. The megafauna of the Pleistocene, woolly mammoths and giant sloths, vanished as climate changed and human hunters emerged on the scene. This interplay between organism and environment is what makes the study of gigantism so compelling. It's a dynamic dance, a constant push and pull where the organism seeks to exploit its surroundings, and the surroundings, in turn, exert selective pressures. The giants are the embodiment of these extreme pressures and opportunities. They are the outliers, the record breakers, the beings that found a way to not just survive, but to dominate on an unparalleled scale. Looking beyond the ancient past to the present, the largest living terrestrial animals, like elephants, still grapple with the fundamental challenges of size. Their massive columnar limbs are designed to bear immense weight, their thick skin helps protect them, and their complex social structures aid in survival and resource acquisition. Yet, even they are relatively modest compared to the true titans of prehistory. The very fact that modern terrestrial giants are significantly smaller than their Mesozoic counterparts speaks volumes about the environmental and physiological constraints that have evolved over geological time. The world today, with its changing climate, fragmented habitats, and human pressures, may simply not be hospitable to truly gargantuan land animals anymore. This leads us to a fascinating area of speculation. What would it take for new giants to evolve? Could future evolutionary pathways lead to creatures that rival the sauropods or the great whales? For terrestrial life, the answer is likely no, at least not without drastic shifts in atmospheric composition or gravitational forces. The square cube law, which dictates that as an object grows in size, its volume, and thus its mass, increases at a faster rate than its surface area, and thus its bone cross-section or muscle strength imposes severe biomechanical limits. Overcoming these limits requires incredibly specialized adaptations, and the energy expenditure becomes astronomical. On land, gravity is an unyielding adversary. In the oceans, however, the possibilities are perhaps greater. If marine productivity were to soar, if vast untapped food sources were to emerge, and if predation pressures were to lessen, perhaps new lineages of marine filter feeders could push the boundaries even further. Could there be an animal larger than the blue whale? The sheer biological efficiency of filter feeding combined with oceanic buoyancy offers the most plausible avenue for continued gigantism on Earth. But even then, there are limits to how efficiently nutrients can be assimilated, how quickly waste can be expelled, and how effectively genes can be passed on. Every metabolic process, every cellular function becomes a monumental undertaking in an organism of immense size. The story of giants is also a story of deep time. Hundreds of millions of years of evolution have shaped these magnificent creatures. From the earliest single-celled organisms through the Cambrian explosion, the age of dinosaurs, and the rise of mammals, the trajectory of life has been punctuated by moments where size became an advantageous strategy. It's a continuum of experimentation, adaptation, and occasional extinction, a reminder that life is never static. The lessons learned from studying these ancient giants inform our understanding of biomechanics, physiology, and ecology on a fundamental level. They force us to reconsider what is possible, what lies at the very edge of biological feasibility. Moreover, the giants of Earth's past and present serve as powerful symbols. They inspire awe, wonder, and a sense of humility. They remind us that we are just one species among millions inhabiting a planet with an incredibly rich and ancient history. Their stories are not just scientific narratives, they are cultural touchstones, sparking our imagination, populating our myths, and driving our quest for knowledge. The dragon of folklore, the sea serpents of legend, the monstrous beasts of our nightmares. Many of these draw their power from the subconscious memory or inspired awe of creatures truly immense. Our ability to reconstruct these ancient lives, to breathe life back into fossilized bones and scattered teeth, is a testament to human ingenuity. Paleontologists, using a blend of scientific rigor and creative inference, piece together the puzzle of prehistory. Every new fossil discovery, every reevaluation of existing evidence adds another brushstroke to the portrait of these colossal beings. We learn about their growth rates from bone histology, their diets from coprolites, fossilized dung, and tooth wear, their movements from trackways and their environments from sedimentary rocks and pollen analysis. It's a grand detective story, spanning continents and eons, with the Earth itself serving as the archive. And in understanding these titans, we gain a deeper appreciation for the delicate balance of ecosystems. When a giant thrives, it reshapes its environment. Communities, perhaps creating vast open grasslands or preventing the dominance of certain tree species. Whales, through their migratory patterns and nutrient cycling, the whale pump hypothesis, play a crucial role in maintaining ocean productivity. The cascading effects of their presence or absence reverberate throughout the food web, influencing countless other species. The loss of a giant, therefore, isn't just the loss of one species. It's a disruption to the entire ecological fabric. This understanding carries particular weight in our modern age, as many of our living giants face unprecedented threats. Elephants, blue whales, giant anteaters, these species are under pressure from habitat loss, poaching, and climate change. Their struggle is a stark reminder that even the largest and most powerful creatures are vulnerable, especially when faced with the relentless impact of a single dominant species. Our own. The lessons from the past, the extinctions of previous giants, serve as cautionary tales. If we appreciate the incredible evolutionary journey that created these magnificent beings, perhaps we can cultivate a stronger imperative to protect those that remain. The story of gigantism is, in essence, a profound meditation on life's capacity for ingenuity. It's about pushing boundaries, overcoming odds, and finding niches where the physically impossible becomes astonishing reality. From the single-celled organisms that first oxygenated our planet, laying the groundwork for complex life, to the towering redwoods that touch the sky and the behemoth whales that cruise the depths, life has repeatedly explored the limits of scale. These giants, both past and present, are not merely biological curiosities. They are embodiments of the Earth's dynamic history, living monuments to evolutionary success, and powerful reminders of the intricate interconnectedness of all life. They silently challenge us to expand our own perspectives, to look beyond the immediate and personal, and to gaze with awe at the grand unfolding narrative of our planet. They whisper of a time when the world was vast and untamed, and creatures of unimaginable scale roamed its surface and plied its waters. And in those whispers, we hear echoes of our own origins, our own small place in the immense sprawling story of life. It's a story that continues to unfold, one that invites us to listen more intently, to learn more deeply, and to protect more fiercely the precious, colossal wonder of the world around us. Our journey into the realm of giants is far from over. With every new discovery, every refined hypothesis, we add another chapter to this epic saga, continuously enriching our understanding of life's boundless potential. And with every passing year, as technology advances, as our understanding of genetics and paleontology deepens, we continue to unearth incredible new details that paint an ever richer picture of these colossal beings. Imagine the thrill of discovering fossilized evidence that suggests an even larger sauropod than Argentinosaurus, or unraveling the complex social structures of ancient megafauna through sophisticated analytical techniques. These aren't just dry scientific endeavors, they are adventures of the mind, journeys through deep time that connect us to a world almost impossibly alien, yet fundamentally linked to our own. The sheer metabolic demands of gigantism are a fascinating area of continuous study. How did these enormous creatures fuel their massive bodies? The logistical challenge of acquiring and processing enough food to sustain a 100-ton animal is staggering. For sauropods, their long necks and specialized teeth suggest a browsing strategy, sweeping through vast tracts of vegetation, a continuous conveyor belt of nourishment. For blue whales, baleen plates represent one of evolution's most elegant solutions to mass feeding, filtering billions of tiny krill from the ocean. Each giant, through natural selection, evolved unique strategies to overcome the thermodynamic hurdles of their immense size. These adaptations weren't just about survival, they were about thriving, about dominating their ecosystems, shaping the very landscapes and seascapes they inhabited. Their presence alone would have altered nutrient cycles, affected seed dispersal, and even influenced weather patterns through their sheer biological mass and activity. Consider also the question of reproduction and longevity. How did these giants ensure the continuation of their species? Slow growth rates and delayed sexual maturity are common traits in large animals, meaning they invest heavily in each offspring. This strategy works well when environmental conditions are stable, but it also makes them incredibly vulnerable to sudden changes. A climate shift, a new predator, or a rapid loss of habitat, any of these could spell disaster for species that take decades to mature and reproduce. This vulnerability highlights the precarious balance of life, especially at the extremes of scale. For marine giants, the vastness of the ocean provides some buffer, a refuge from immediate threats. But even there, the impact of human activities, from plastic pollution to industrial whaling, has shown how quickly these magnificent populations can be pushed to the brink. The enduring mystery and allure of giants also extends to our cultural psyche. From myths of dragons and sea monsters to the legends of colossal beasts, humanity has always been captivated by the idea of something far larger and more powerful than ourselves. These stories, passed down through generations, are perhaps echoes of an ancestral memory, a primal understanding of a world once populated by creatures that dwarfed human beings. They serve as a testament to the profound impact these animals have had, not just on the ecological stage, but on the very fabric of human imagination and storytelling. Ultimately, the study of gigantism isn't just about the past, it's intrinsically linked to our future. What can we learn from the demise of the largest creatures? What lessons do the struggles of today's endangered giants offer us? The answers compel us to rethink our relationship with the natural world, to move beyond exploitation and embrace stewardship. It's a call to understand that the health of the planet, and by extension our own well-being, is deeply intertwined with the fate of these colossal wonders. Their continued existence is a barometer of ecological health, a living testament to the richness and resilience of life on Earth. To protect them is to protect the intricate web of life that sustains us all, and to ensure that the epic tale of gigantism continues to unfold, not just in the fossil record, but in the vibrant living world we inhabit today. The grand narrative of life's scale, from the microscopic to the colossal, is a story we are still writing, and we have a fundamental role in shaping its next chapters. Let us write them with wisdom, respect, and a profound sense of wonder.